Okay, we're going to start part 3 of the class and discuss mostly topics concerning hypothesis testing. So let's begin by talking about what we mean here. So suppose a city needs sewer pipe, and they decide that the breaking strength of their pipe should be greater than 2,400 pounds per square inch. So for a particular pipe vendor that wants to sell a sewer pipe, we must be convinced as city officials that their company's pipe performs better than 2,400 pounds per square inch. So what might we do? Well, we might ask them for 50 pipes that we can test and begin our analysis. So we test 50 pipes, we get an average strength for their pipes, and a standard deviation there. So notice the average strength here for the pipes is actually greater than our spec of 2,400 pounds per square inch. And a knee-jerk reaction might be to say, well, they succeed. Their pipes succeeded, and therefore we should buy their pipes. But the problem with this idea is that we don't know necessarily. They might have 10,000 pipes in their storehouse, and we happen to pick 50 pipes out of that 10,000 that were exceptionally strong. Possibly we picked 50 pipes that were weak, but we don't know where those pipes are going to fall. And if you remember the central limit theorem, we could create a sample mean distribution. You know, suppose we did this test 100 times, then the variable for this distribution would be the mean of 50 samples. And if we did it enough, we could find the true mean of the population in their storehouse. And if that true mean was greater than 2,400 pounds per square inch, then we would be happy and satisfied that their pipe was good enough for us to buy. But the problem is that the company's only going to give us 50 samples to test. So now we have to decide with these 50 samples, we have to come up with a way to be convinced what the mean of the samples are in their warehouse's population. So it's possible that, for example, that the mean that we pull here with this X bar could be way over here on this end of the curve in the distribution of strengths associated with their pipes in their storehouse. And that would mean this population mean for this sample mean would be so if this was, say, like 2,460 over here, this is going to be much less. So on average, the pipes in the storehouse are going to perform much poorer than this, and possibly below the spec of 2,400 psi. You know, on the other hand, we could end up this could be over here, and the mean for the population in the storehouse could be somewhere to the right of this. We just don't know. So what we're going to have to do is come up with a way to evaluate this mathematically and try to determine what the mean is for the population in the mean is for the population mean of, so I'm going to call this mean sub X bar like we did before, and this is the mean for their population. We need to figure out what this mean is, or come up with a way to be confident that that mean is at least greater than 2,400 psi. And keep in mind, the mean for the population mean of pipes in their warehouse should be equal to this mean here for our sample means distribution. So the question is mu for their population greater than 2400 psi? Well, the way we're going to address this question is through a process called hypothesis testing. So this is going to give us a decision-making process for evaluating claims. In particular, the vendors claim that their pipe has a strength greater than 2400. And the approach we're going to use is we set up two hypotheses. One hypothesis is that the mean of their pipes is greater than 2400 psi. The other hypothesis is that the mean for the pipes strength stored in their warehouse is not greater than, but less than or equal to 2400. But I'm just going to put equal to 2400 psi, and this just implies less than or equal to 2400 psi. But for the sake of simplicity, we're just going to say that the mean equals 2400 psi is our null hypothesis. So we have a null hypothesis and an alternate hypothesis, both of which can't be true at the same time. So one or the other is true. And mathematically, we're going to make a determination of which one of these is true. So we need some form of convincing evidence before we can conclude that the vendor's pipe mean strength exceeds 2400 psi. And we need to be sure that this is an actuality and not just, well, we need to be convinced that this is an actuality and not just some result of sample variance, where possibly the 50 pipes that we took maybe were pulled from, just happened to be pulled from really strong pipes in what was otherwise weak a warehouse full of weak pipes. So we actually might want to we might want to be 99% sure, for example. Okay, so we can approach this in a similar way that we approached our confidence intervals. So let's relate all this to standard normal curves. Since we're using samples taken from a population, we know that if we have a large enough sample that ultimately the sample mean distribution is going to be a normal distribution. If that's a normal distribution, we can relate it to a standard normal curve, and we can figure things out concerning the areas involved. In particular, for this problem, we're talking about a situation where we're looking at 99% of information under this curve, which means that this area over here is only 1% left. So we could take our information that we get, our mean for our sample, and we can relate this to z, and we can figure out what the z term is for a 99%. So when we're talking 99%, we know that the z associated with the area of 99% to the left in a standard normal curve, we know this z is 2.58. Now you can find that yourself by going to the standard normal curve and looking at 99% and figuring out what z value this is, or you can look back on those tables, those shortcut tables I wrote in previous lectures. But 2.58 is a z value here, and this is like a critical, we might call this the critical z value. And what we're going to do then is we're going to calculate a test statistic or test value of z. So let's call this z sub t, a test value of z, and we're going to look and see where it falls.